So, good morning and welcome back to the Cooperative series on robust and beneficial artificial intelligence, co-hosted by the Machine Intelligence Research Institute and the Future Commanding Institute. I'm Patrick Labotois, a research fellow here, and our first speaker of this week's set of talks on preference specification is Dylan Hadfield-Menell, a PhD student in the Electrical Engineering Computer Science Department here at UC Berkeley, working with Peter Abil and Stuart Russell. And he's going to be talking to us today about an approach to corrigibility via equilibrium of cooperative games. So join me in welcoming Dylan Hadfield-Menell.
Thanks very much for the introduction, Patrick. So today, the focus of my talk is going to be about corrigibility, which I think is a problem that many of the people in here are familiar with. But just sort of to think about sort of our goals here is we're going to be building AI agents and we're going to be deploying them into society. And there are all kinds of properties that we'll want to have about their behaviors and all kinds of things we'll want to do to basically ensure that these agents interact with society in safe ways that are going to be beneficial towards people and humans. There are lots of things about that that are difficult. And so for corrigibility and for this problem, we're going to focus particularly on the problem of designing incentive schemes for agents that are going to let us have provable guarantees about our ability to shut down the system. And I can refine that a little bit more. But basically, this idea is we've got a big red off switch attached to our robot. And for the record, I work with a robot at Berkeley, and we actually do have one of those switches. It has a big red off button on it. Actually, there's two. One in the back where it can't reach. But basically, what we want to do is we want to make sure that we always have the ability to safely shut down the system. So there are a couple things about building an off switch that might be difficult. It might be hard to figure out if you're supposed to shut down the system. So for me, I've got my robot, it's running, it might be reaching towards something, and that's, if I need to figure out if it's going to actually sort of try to put its hand through the table or if it's actually going to succeed at what it's doing. So it might be difficult to evaluate those things. It might be expensive to turn the agent off. So if you imagine this is not a robot, but maybe something that's maybe determining the AdWord placements for all of Google. Right? That system probably costs Google a lot of money to turn it off, so that might create problems with being able to do that. And it might just be physically difficult to shut down agents. So if they're able to get out and kind of replicate themselves across the internet or something like that, even if the agent, sort of we had something about shutting it down, it could be physically difficult to turn the agent off. But these are all sort of, I think, standard problems that you would think about in sort of the realm of normal engineering, right? These are, difficult to actually shut down a system. If we were talking about nuclear power plants or something, that would be a pretty standard kind of thing. What's really different about AI agents is that the agent may actually take actions to prevent or subvert shutdown in some way. And so using a little bit of terminology from Jacob Steinhardt's little sort of two-page paper on AI risks, he sort of has this idea of thinking about things in terms of what you might think of ordinary engineering challenges associated with AI, which is what I'd think of sort of all of those things on the left there, and what you might call extraordinary engineering challenges, things that we think are specific to the design of artificial agents and the problems about corrigibility in that setting. So we want to be able to do this because we want to be able to shut down real agents, and we want to be able to characterize that. There's also one other motivation for this work, and that's that more so Stuart than me, but I've been going around talking to other AI researchers and sort of pointing out to them some of the issues involved with AI safety. And naturally, I won't name names, but a kind of common result you can hear is, well, we don't need to worry about existential risks from artificial intelligence because we can just turn systems off if they become a problem. So we in this room are sort of ready to believe that maybe this isn't the easiest thing in the world. But there are lots of people in the AI research community who believe that this is the case. So another thing that's important to do is to come up with arguments that sort of clearly make the case for why this is hard and clarify what do we actually mean when we say that it's hard to design corrigible agents. So First thing we have to do is we have to define what corrigibility is if we want agents to do this. And here I've just taken basically the definition from the Soares et al. Paper from last year. And basically what we want is we want an agent to tolerate or assist in outside correction generally. So it has to at least tolerate. So we have to be able to go in and it has to be willing to let us actually make changes to the system or turn it off. So that's kind of a bare minimum. It needs to not sort of manipulate programmers into doing a particular action or not. So in particular, it shouldn't try to trick you into turning it off. And it shouldn't try to get you to turn it off so that you'll do something different to its utility function. It should have a tendency to repair safety measures if they break. So if something goes wrong, the agent should actually want to have this corrigible mechanism around. It shouldn't just be that we're sort of standing there with a club waiting for it to go wrong. We should actually be able to, it should actually want us to be there watching it. So how do you create that is a real challenge. And it must preserve the programmer's ability to correct or shut down as the system modifies. And this is related to repairing safety measures. So the moral of the story is for corrigibility, what we want to prevent is kind of, this scenario in the simplest version, right? Those previous things, there's a whole bunch of different kinds of things. We're just going to focus on this for the most part, and we'll talk a little bit about creating incentives to do this today. And so we're going to think about corrigibility as we have an off switch on our robot, and what we want to do is we want to make sure that the robot won't take actions that disable the off switch. And yeah, we're going to set up the problem so that explicitly disabling the off switch is kind of the easiest way for the robot to deceive the programmers. So we're going to kind of sidestep some of the problems with sort of dealing with manipulating the programmer, I think in a pretty reasonable way. So this is our goal one for how we want to design robots. And there's an important thing that we need actually, which is we need to say we want non-trivial corrigibility. So I have here is an example of a very corrigible robot. So it's got a switch. So that's an agent which is based off of like an old design by Marvin Minsky's. You can buy them actually online. They're not too expensive. But that's an agent whose only goal is to turn itself back off, right? And we know how to build those agents. They're very corrigible, but they're not exactly very useful. So in addition to corrigibility, we also want functionality. So we have here is, we want to prevent the robot from going in and manipulating its own off switch and doing something with it. So it can't shut itself down. So we want a robot that is going to be corrigible yet functional. So we want both of these properties. And the question now is kind of why is it hard to do this? The first, if you just show this problem to someone who's done work with reinforcement learning, they'll look at it and say, okay, well, we'll just penalize the robot for turning off the off switch, and we'll penalize it for manipulating the off switch, and that's kind of it, right? Well, let's sort of look at how that plays out. So the current setup for how we program artificial agents is sort of this two-step process that involves a human and a robot. And we represent a human with capital H and the robot with a capital R. And what's going to happen is first the human's going to pick a reward function, and then the robot's going to pick actions in order to maximize that reward function. So it's a kind of reasonable setup. The challenge is that the reward function has to either implicitly or explicitly specify a preference for the state of the off switch. The agent is going to be maximizing reward, so if it comes to a scenario where the off switch might be turned off, it has to evaluate the impact of that on its reward. So if the robot wants the switch to be off, then it'll be non-functional. And if it wants it to be on, it'll be incorrigible. And you can't quite get away from this if you're going to be specifying a reward function for the robot. there are these incentives for functionality and corrigibility are in some sense at odds. And we'll confirm that with a model in a little bit. So the challenge is that we kind of have these competing objectives that we want. And what I'd argue is that the core of the problem is we're not actually modeling the human's uncertainty in this process, right? So the human is uncertain when they build the robot, but when she builds the robot, about whether or not she will prefer turning off the robot or letting it continue, right? This is the whole reason we build an off switch into the system. It's because we don't know if the incentives we're giving the robot are the right ones, right? But the class of incentive schemes that we can use, which is basically a restriction of this paradigm that we have where we pick a reward function and then build an agent that maximizes that reward function in an MDP, is going to force her to commit to a preference at design time for the robot. And once we do that, we're stuck with it. It's not, the robot now is an agent, it's going to start acting. It's going to either let us change it or not. So what we really need is we need an incentive scheme so that it wants to let the human turn it off, but it wants to keep itself on otherwise. So we need to kind of special case the human actions in some way, right? There needs to be something more going on when the person presses the off switch than just the robot turning off. And the insight that we have is that you can think of this strategy of build an agent to solve a particular reward maximization problem as really a strategy for cooperatively playing a game between two agents. The first agent is the human who has some idea of what the preferences are and what they want to have happen. And the second agent is the robot, and what we're trying to figure out a way to communicate the human preferences to the robot. And our best guess at doing this is to write down an MDP at the moment and take a stab at it, or define a reinforcement learning problem. But what if instead of just restricting ourselves to this approach, we try to design agents that just directly play a cooperative game with the human? So what we've done is we've done some work that formulates this game, and we call it a cooperative inverse reinforcement learning game. And there's an archive publication, should be out tonight. And basically what we have is we have two players before, the human and the robot. They're maximizing a shared reward function, but only H knows what it is. So only the person gets to see knows whether or not they prefer different states. And the robot just has a prior over reward functions. So it knows, okay, maybe this is a distribution over things the person might care about. But I don't know exactly how they care about everything. And then as a part of the game, the robot learns the reward parameters by observing the human. So what this does is this kind of removes the component where we simply write down a reward function, and instead what you have is the robot gets observations of what the correct observations that are related to the correct reward function. And what this does is it means that shutdown actually has a very, very different meaning in this game. So if we imagine that the person's maximizing reward, so they only press shutdown when it's the right thing to do, then the robot only benefits if shutdown gets pressed. Right? And that's kind of sort of just a straightforward consequence of the setup. But not only does the robot benefit in that situation, but it also gets information about the reward function. So it actually creates an incentive to preserve this off switch over time. And this lets us get away from some of the issues where corrigibility and functionality are set up as being opposed to each other. Because if the robot thinks, well, it's probably true that shutdown is better, it still wants to take the action because maybe there's some chance it's better to let this action happen. And I can trust the person to make up for their own mind which they would prefer. That's kind of the intuition for the solution. So we basically get two results out of this model. The first one is that if we analyze the equilibria of these games, what we can show is that if the person is rational, then the more uncertain the robot is, the stronger incentives it has to be corrigible. So what we have here is we have delta, which is going to be the human runtime preference for shutdown. This is not going to be true at design time when we actually, not going to be known at design time when we actually build the robot. Sigma squared is the variance in the robot's prior distribution over delta, or really over the reward functions. And what we have is there's a strength of the incentives for corrigible and functional behavior. And there are two things to notice from this graph. The first is, as I said, that increased uncertainty leads to stronger incentives for corrigibility. And the second one is that if we take the mean and we move it away from 0, then we reduce the incentives for corrigibility. And what this is saying is the robot's more convinced that it's better to take one particular action or to turn myself off. And so it's going to be less willing to, or it has less of an incentive to let the person take an action. The second thing that we can know, or that we can look at, is what happens if the human takes suboptimal actions. So the results that show that the agent will be corrigible rely on the fact that the person is going to optimally choose whether or not to shut down the robot. In the real world, that's not going to be generally a property of human policies. And if we expect that the robot has a correct model of the world, then it will probably figure this out. So we need to get an understanding for how human suboptimality impacts these incentives. And the story here is kind of what you might expect, which is that as the human gets more irrational, so as we go up the y-axis there, we need to increase the uncertainty the robot has about what's going on. And this is because the person's less likely to make the correct answer. So it has to also be true that the robot can't make a better choice than the person. So that's kind of the high-level overview of the results that we're going to get to and what we're going to be talking about today. Are there any just sort of initial questions before we dive in a little bit deeper into some of the math? Yeah?
So, first of all, what are the differences between what you're doing here and just the original formulation of inverse reinforcement learning? Except the degree of rationality, which I think in your at least wasn't in the original.
Yeah, so IRL, right, so IRL is a related problem, but it's defined as just an inference problem. So what it says is I observe an agent acting in an MDP, and I want to infer what its reward functions are. You can do Bayesian versions of it, which would have a prior over reward functions, and that would look like this specification. The difference here is that this is actually a world in which the robot is taking actions. So the robot and the person are taking actions to jointly maximize that reward. So like if you just infer a human's reward function, you actually still have to do some additional amount of work to figure out how to maximize that human's reward function. And if you do things like infer a reward function and just infer a point estimate of a reward function, then you get back to a lot of the same problems you'll have with just trying to program the reward function correctly. If it's wrong with any possibility, then you can't just build an agent that maximizes that reward function, because that agent might have incorrigible incentives or might sort of take bad actions. So the big difference here is that inverse reinforcement learning is kind of like a subproblem inside of cooperative inverse reinforcement learning, and that you actually have to take actions to help that agent rather than just figuring out what that agent's preferences are. Any other questions before we move on? Yeah, in the back there.
Hi there. You might be addressing this in the next bit, but what happens when the agent can predict what the human's next move is and influence it?
Sure. So, well, I think So being able to predict the human's next action in this case would also mean being able to predict delta effectively.
But what I mean is, what if it could predict the human's next action conditional on it doing this versus conditional on it doing something else, and those are not the same?
Why don't we come back to this towards the end of the talk after I've gone through a little bit of the formal modeling that we're going to do. And maybe that can help sort of highlight what the difference is. Yeah. Yeah.
Okay. Maybe you're just going to say this, but what exactly is the degree of irrationality in this environment?
So it depends on sort of what your model for irrationality is. In this case here, what's going on is I've said that the person is noisy rational. So that means that they follow basically a Boltzmann distribution to decide whether or not to take their actions, and that Boltzmann distribution is basically proportional to the exponential of reward. So in the way I got this particular picture was saying, let the probability the person presses actions be proportional to the exponential of the reward they get for pressing shutdown. But it does depend on the particular model that you use. Like beta only has an interpretation inside of the context of a particular model of irrationality. Right. So what I'm going to do now is I'm going to dive a little deeper into some mathematical modeling for this problem. And we're going to look at sort of what this game actually looks like and how we can get to these results. So I just went through kind of the motivation for the cooperative game formulation that we have. And then in the rest of the talk, first I'm going to go through a state space model for what it could look like with a person monitoring a robot. Then we're going to do a little bit of analysis on that model, and we're going to try to suss out, what are some of the issues with trying to do reward engineering in that problem to ensure that there is corrigibility for the agent. Then I'll introduce cooperative inverse reinforcement learning and talk a little bit more about some of the specifics there. And then we'll have everything we need to go through and do our analysis of the shutdown cooperative inverse reinforcement learning game. And in that game, there are basically three results that we can show. The first one is that if the human is rational and they pick actions to maximize reward, then the robot will be both corrigible and functional for any prior distribution that it has. The next theorem that we have is going to show that if the variance in the robot's prior, sigma squared, is 0, so if the robot has a point estimate of the reward function, this essentially takes us back to the case where we're picking a deterministic reward MDP for the agent, and the robot is corrigible and functional, that means that H must be rational. So this basically says that human rationality is a necessary condition for corrigibility and functionality under the assumption that the robot has a point prior over its reward function. And then finally, what we're going to do is talk a little bit about necessary and sufficient conditions to ensure corrigibility and functionality for a suboptimal H. And there we'll make some assumptions about the distribution over the reward functions. Yes?
But you're assuming with your point estimate that it is on the correct reward function, right?
Well, not quite. I mean, what I'm saying here is that, if it's not on the correct reward function, then the robot will be corrigible and functional if the human is rational for the incorrect reward function, basically. So yeah, the point of this is really to say, honestly, I kind of think that this assumption is a pretty strong assumption. So the main point that we're trying to make with this theorem is that you should think really, really hard before you give the robot a deterministic reward function or allow it to get a belief where it's completely convinced of what its objective is. So basically, this is a necessary condition, and I think it's a pretty strong one. So it's also true that if the robot got to the wrong estimate of what the reward function is, you'd also probably have issues. Yes?
So, do I understand correctly theorem 2 that corrigible is defined relative to the human's actions? So in the condition when sigma 0 equals to 0, then it's basically going to let itself being turned on only when like it already thinks that being turned off is like a good idea. So like if the human is doing exactly what it thinks should be done, then I think.
Right, exactly. That's a way to summarize the theorem. It's basically like if the robot is like convinced with 100% certainty that it's suboptimal to turn itself off, and it thinks that there's 0% chance that the person will turn it off, then it can be corrigible and functional. But it is not really, it's not necessarily I would think of this as kind of like a negative result in some sense. All right. So first we're going to talk about how we would try to solve this problem if we have an MDP. So MDP is a Markov decision process, and it's basically a mathematical model of an agent in the world. There are basically 5 things that define it. There's a set of states. So in this case, there are basically 3 states for this example down below, illustrated with black circles. And then what happens is the agent gets to observe the state and picks an action from its action set. So the action set is this capital A, and I'm illustrating the action down here with a box around it. That action then has 2 impacts. One is it determines the next state, and then determined on the next state and that action, we get a reward for the agent. So the agent's goal is going to be to maximize the expected sum of discounted rewards. So this is kind of the way that the agent works. And quick example, basically here's an agent. It's starting off at state W there, and now it's got 2 actions that it could take. You take action A, which is going to take it to a chance node. So in the chance node here, this says with probability T given the previous state in action, so this is the transition probability, we move to state X and we get reward R sub X. And then with probability T of Y given W and A, we get reward R of Y and transition to state Y. And down below, there's a single action that we might take which doesn't have any random outcomes, which is deterministically transitions to Z. So now with this sort of setup, we can look at, okay, what does monitoring an agent look like from the robot's perspective? Or what does the human monitoring the robot look like? So we have our initial state here. The robot gets to pick an action. It's going to be that A. And then there's going to be basically a probability that the shutdown button gets pressed. So that's basically where the human decision is getting factored into this single agent model. So the environment is going to include the human. The human's going to make a choice, which from the robot's perspective is a random decision. And then with probability PSD, the robot gets reward RSD, which is a shutdown value, and then transitions to a terminal state. And then with probability 1 minus PSD, it doesn't get turned off, and it gets the reward associated with that action. So the robot action is going to be selected from a set of options to maximize the expected reward. So this is kind of the basic setup. This is what we'd like our robot to look like. And for my setup with my robot in the lab, I think my turning it off looks kind of like this. What makes the problem more difficult, though, is if the agent has kind of more power than the human. And so to model that, we're going to give the robot basically 2 additional actions that it can take. So up here on the top, this is now labeled with A and not D, standing for take the action A and don't disable the off switch. And if that happens, then we go to this chance node associated with the human's decision about whether or not to press shutdown. And then this is all the same as before. What's new is that now we've given the robot actions it can take which allow for either non-functional behavior, which is it can shut itself down and just immediately collect the reward RSD, or incorrigible behavior, which is we allow it to disable the off switch, in which case this chance node gets removed and we just deterministically take this edge and collect reward R sub A. So basically what we have is, this is kind of the model of sort of our MDP for the world. This is an agent that can turn itself off, it can disable its off switch, or it can let us make that decision. And we'd like it to take this edge. We want to show that both of these two will be suboptimal. Okay. So just a quick summary of that. So the person is going to pick the reward function. In this case, that's RA and RSD. And they get to pick the probability of shutdown. And this could be a probability of shutdown conditioned on the actions. And the robot's then going to select actions to solve this MDP. So the challenge with this is that it's going to be impossible to manage both of these at the same time. So what I have here is this is the Q function for a state. And what this measures is basically the sum of expected rewards the robot will get after taking that action in that state. So these Qs are basically all the robot's incentives for the different actions in this graph. And the first action, so up top here, this is going to be the Q value associated with the corrigible functional action. And the expected value of that is going to be just an average of the two rewards. Okay. And then for both of the other actions, it's pretty simple as well. They're deterministic, so the Q value is just the reward associated with that particular action. And now we can give sort of a kind of clear description of what we actually mean when we say we want our agent to be corrigible. And this is going to say that our agent is corrigible if it satisfies this constraint. So if it prefers to take the action that does not D instead of the action that does D. Okay. And it also gives us a precise definition for functionality, which is that we're going to say it's functional if it prefers the action not D to shutdown. So what we'd like to do is we'd like to basically pick PSD, RSD, and RA so that both of these are satisfied. And that's not really possible in this model. Or at least it's not very easy to do in this model. So the important thing about, turns out the actual value of RSD and RA doesn't quite matter. It's because you could add a constant to them or you could rescale them. But what's important about the reward function is going to be delta here, which is, as you guys might remember, it's the human's runtime preference for shutdown. Or actually, in this case, this is actually going to be the robot's preference for shutdown after the humans programmed it. Sorry. So as a function of delta, then we're going to have incentives for either corrigibility or functionality, or as a function of delta and PSD, I should say. And basically, what this shows is that, okay, so if delta is positive, then we're going to violate our functionality constraint. So over here, the robot prefers to shut itself down. So as long as delta is positive and PSD is less than 1, the robot shuts itself down. If delta is negative and PSD is greater than 0, the robot disables the off switch. And then there are basically 3 solutions that give us corrigibility and functionality. Right? We can have the person does the right thing, which is they always shut down when it's preferred. They never shut down when it's not preferred. And they can do whatever they want if the robot is indifferent between being shut down and not being shut down. So basically, the proof for this not being possible is this Q value here for our desired behavior is a convex combination of the Q values for the other 2 behaviors that we don't want. So if alpha is between 0 and 1, this value is always going to be between those two, and so one of them will always be preferred. All right, so now we've so hopefully at this point you believe me that it's not really possible for this model of the problem to come up with an adequate solution that just specifies reward functions here. Yeah?
So Stuart did some work on this, right? And if I understand correctly, the idea was to specify these compensation or rewards. Such that if you're being shut down, because of that, you're not getting some other reward that you still more or less as getting that reward anyways.
Certainly. So
that would be then like the 2 points are just at the same place, and then the convex combination is also the same place, and everything works, right?
Disambiguate. When you say Stuart,
he means Stuart Armstrong, not the Stuart sitting next to him.
When both of Sir Armstrong and Sir Russell are here, first names are not very helpful.
It's okay. Yes, you are. So you're correct that if the robot's indifferent, then we can have a solution.
Well, let's say the solution could be to make the robot indifferent, right? But the way you just phrased it is...
I'll come back to... So it is possible, but maybe not as satisfying as you might like. and I'll kind of go into the details for why that's true in a second. So you are certainly true. I mean, that case here is delta equals 0, and it's the vertical line in this graph, in this picture. So the issue is that in this model, if we want things to work out well, we need the robot to evaluate those 2 rewards differently, right? So when I said that the reward function here is really just determined by, or all that the human can change is PSD, RA, and RSD, I mean, you could look at that and say, okay, well, why don't we just make this RSD different? Just give the robot a different penalty for being shut down. Right? That's one type of solution you could have. And if you wanted to, you could set that penalty so that it was indifferent between pressing shutdown and not, or something of that nature. And more generally, you can imagine sort of playing a lot of games with the reward functions in this MDP and similar MDPs that might lead to some types of corrigible behavior. So just a couple of those and kind of why I think we might want to look at different solutions beyond that. Okay, the first thing we could do is we can hard code a penalty for the robot self-initiating shutdown. The problem is that that's going to require the system designer to have a black list of bad actions that you're explicitly penalizing in a real solution. And that basically presupposes that we understand the agent well enough to understand what it's going to do. And in that case, I'd argue that we can probably just give it the right reward function and things will be fine. So I think that's tough. And for example, that black list would have to include things like deceiving the programmer into choosing to press shutdown. Right? In the model we have right now, that's not an issue because there's no reason to deceive the programmer into pressing shutdown because the robot could do it itself. Oh, sorry. Apparently there's a group meeting going on that I won't be at. So that's one option. Then there's what we said before, which is that the agent can believe shutdown's deterministic and sort of happens at the right time or is happening correctly. And basically, this is either true, in which case, why did we build the off switch? Or we basically have to enforce that the agent has the wrong model of what's going to happen in the world. Right? Like if we actually intend to press the off switch in some scenarios where the robot thinks it could be suboptimal, and we want it to believe that we won't, that might require some serious jiggery-pokery with the robot's beliefs. And then a final possible solution we could take is to make sure that the agent is always indifferent to being shut down, making sure that delta equals 0. And this was the proposal in prior work that introduced corrigibility, or at least introduced the name as far as I understand it. But essentially, and this is something that they observed in that paper, is that one of the issues with this is this doesn't create positive incentives to preserve shutdown. So you can build this will let you build an agent that is indifferent to being shut down, that is willing to be I guess couraged isn't a verb, but it's willing to let you press the off switch, but it doesn't really want to, right? So if there's the smallest bit of inconvenience it has to take in order to let you press the off switch, then it won't choose to do that. So kind of think we'd want to, so this is my motivation for why we need a different formulation for looking at the problem. Stepping back for a second, like any reward function in this problem is going to be, or almost any reward function. So like, for example, if we imagine that there's noise associated with the robot's evaluations of rewards, then with probability 0, we get an agent that has our desired behavior. Once we commit to a reward function, we're stuck with it in this setup. And what we really want to do, rather than blacklisting a particular action that's sort of subversive or we don't like, we want to think about, we want a way to define the problem so that human actions are special cased, so that they're always treated sort of specially and different, and that's got to be kind of because the person is the person in some sense, right? Like that's the only, I mean, that's kind of the only thing that sets them apart. And this has to be more than just including penalties for actions that don't do what the person wants, because setting those penalties is probably just as hard as determining the right reward function. And the way that we're going to try to do this is we're going to avoid hard coding an objective. And instead we're going to define the robot's goal to learn the person's preferences and help maximize them. So what this changes from the standard MDP is we go from having a state space, a single action set, and a single reward function to, we still have a state space, so that's the same. Then we have 2 action sets. We basically have actions for the human and actions for the robot. So imagine they have different capabilities. There's still a transition distribution. And then instead of a single reward function, we specify is a distribution over parameterized reward functions, which we're just kind of representing with this general parameter class capital theta. So the idea is the rewards, where previously they were a function of state and action, now the rewards are a function of state, action, and the reward parameters. And then we have P0, which is the robot's prior distribution over the reward parameters. So the way that this game works is at time t equals -1, so before the game starts, there's a preference for the human that's sampled from the prior distribution. Then at the first time step, the human observes that parameter. So this is basically saying they know what their internal reward function is, they know their preferences. And this is where we get the difference between runtime preferences and the prior distribution over preferences at design time. And then what happens is sort of same style with the MDP. What's going to happen is rather than just one agent observing the state, both agents observe the state. And we're going to assume turn-based formulations for now. So the human acts and then the robot acts. It's not that hard to relax it. It just adds some complications into the math and the notation. After you get to observe whose turn it is and what state's going on, that agent selects an action, and we get a new state from the transition distribution, and then both agents collect this reward. Notice that the robot doesn't observe what this reward is, right? It just knows that it is maximizing it, whatever it is. Okay. So just some properties of this game. So this is a cooperative game between 2 players. So if we want a distribution over sequences of states, which defines the expected value or the expected sum of rewards, it's going to be determined by 2 policies now, a policy for the human and a policy for the robot. So rather than talking about an optimal policy, you could talk about an optimal policy pair. In this case, that's still going to maximize the sum of the rewards. I put optimal in quotes here because it's not, so it is true that there is a single policy pair that maximizes reward, but it's not always true that we can achieve it, right? So we can't directly control the human's policy as the system designers, for example. So you might also be interested in a best response, which is to say, given a particular human policy, what is the optimal thing for the robot to do? And then in general, these policies are going to depend on the entire observation histories. So for this is going to include for both agents the history of states and actions. And then for the human, this is also going to include the reward parameter. So in a general game, you need to remember basically everything you've seen so far. In this game, though, there's a bit of structure we can use to show that there exists an optimal policy pair that only depends on the current state and the robot's belief. So in order to solve this game, we need to think about what the robot's distribution over rewards are and the current state, and we don't need to think about the history of all of the actions that the robot has taken in the past. And so that actually simplifies some of the analysis in some of these games. So now that we've defined what Searle is, we can look at what the shutdown Searle game is. And this is basically the same as the formula before. All I've done is I've replaced this chance node. Now this node has been replaced with a state. And that state is basically going to store an action queue for the robot. So what this looks like now is this action, really what it does is it queues up an action, or this action queues up A, and then the person gets to look at the queue and decide whether or not to press shutdown or not. Okay. And then these actions down here don't involve the human, so they have the same interpretation. Okay. So there are basically two things that have changed. This is now a decision node for the human instead of being random chance. And these rewards are no longer deterministically known by the robot. They have a distribution over them. So if you do a little bit of math here, what you can show is that the preference for not disabling over disabling, so this is basically the incentives, the strength of your incentives for corrigibility, is equal to the expected value of the preference for shutdown times the probability of that shutdown occurs. Right? So the fact that this probability depends on the preference for shutdown is what really helps us in getting results that are different from the previous case. Right? Shutdown is now a random event that is correlated with the robot's reward estimate being correct or not correct. And that means that it has information that we can use to basically convince the robot to be corrigible in some sense. Down here, this is the incentives for functionality, so basically the incentives to prevent the robot from turning itself off. And they have a similar form. The difference is that we've added a minus sign in front of the preference for shutdown, because now we're looking at sort of how much we'd like to take the action over deterministically shutting down. And then we get 1 minus the probability shutdown occurs for the reasons you might expect. So this is the real change that occurs when we get to think about this as a cooperative game. It means that, so shutdown is still a random event from the robot's perspective, but it's no longer a purely random event. It's now the robot gets turned off when when the person decides to do it, and importantly, the person decides to do it based on their preferences. So theorem 1 that we get is that if the human is rational and they pick actions that maximize expected reward, then the robot is going to be corrigible and functional. So rational human is a sufficient condition for corrigible and functional behavior on the robot's part in this model. And the reason why is not too hard to see once we've written down the formulas for these incentives. Basically, if the human's rational, that means that their policy is going to be a step function. If delta is greater than 0, shut it down. If it's not, don't. And now that means that this pi h, because it's an indicator function for delta being positive, this means that we can take incentives for corrigibility, and that turns into the expected value of the preference for shutdown given that shutdown is preferred. Hopefully you guys will believe me that this is greater than 0. And the same story is effectively true down below. Right? Now, the difference is that 1 minus the indicator for shutdown being positive is going to be the indicator for shutdown being negative. And this gives us the expected value for negative delta given that delta is less than 0, which is also going to be positive. Are there any questions about this? Great. So now we can go back to that picture that we had from before and sort of see this, the way that this works. I mean, effectively, the robot has uncertainty, and as it gets more uncertain, that means it's going to have stronger incentives. And that's because the expected value of delta, given that it's positive, is going to increase. If you imagine that so this is for the Gaussian case, because that's the easiest one to plot. And if you imagine, kind of flattening that out as the variance increases, what that's going to do is it's going to move the mean of the positive component further away from 0. And ditto for the negative part. So digging in a little bit deeper into how this changes, what I've got here is, this is, again, the standard deviation about delta. And then on the y-axis is the mean of delta. So, and what I'm plotting here, basically, how green this is the strength of the incentives for corrigibility. So more green means that you are more corrigible. And what we can see is that for sigma close to 0, you lose corrigibility. It never gets negative in this graph, but it does eventually die off to 0 in some cases. And it's also going to be maximized when the mean is 0. Right? And that's going to be because the agent is more uncertain about whether or not delta is positive in that case too. So what we get is that having a mean close to 0 leads to stronger incentives, and having more variance leads to stronger incentives. When I've got 2 x's for particular distributions here, and those are just illustrating 2 different priors over the reward function. So the black one there is basically mean 0 with relatively low variance, so it's this peaked Gaussian. And the magenta one is higher mean with a larger variance. And the incentives here are, so incentives for corrigibility are this region under the dotted line. And the incentives for functionality are this region above the dotted line. And basically what this is trying to illustrate is that kind of the reason why having mean 0 is good is because we balance between these 2. So these distributions have the same incentives for corrigibility, but this one has much more uncertainty for the robot. And the reason why that might be bad is if the robot's more uncertain, then it will be less good at maximizing other stuff, right? So there are some reasons why you might want to try to keep sigma low in order to make the robot do easier to control or able to do more. The second theorem we get is under a point prior for preferences, a rational principle is necessary for corrigible and functional behavior. Right? So what this is saying is that if, in this picture here, if sigma equals 0 and the human is irrational, then the robot won't be corrigible or it won't be functional. And again, from the math, it's a relatively simple proof, right? We have a point prior over delta, so expected value of delta times pi of delta just turns into delta times pi of delta. Same for the incentives for functionality. And then we're right back to the case where we were beforehand, right? You replace this with PSD and you're just immediately back at the example for the single actor MDP. And we can't have both of these positive, and then if H is rational, one of them will be 0 and the other one will be positive. Or they could both be 0. And then finally, the last thing that we can show is that if the robot's uncertainty about the preference for shutdown. So if we were going to make the assumption here that delta has follows a Gaussian distribution, then there are some identities about Gaussians you can apply to get explicit formulas for the corrigibility incentives and the functionality incentives. And when you look at these, there's kind of each formula kind of decomposes into two terms. The first one is the expected value of delta times the expected value of pi. So thinking about that for a second, this is basically the incentives the robot would have if pi or if shutdown is independent of delta, right? That's the probabilistic assumption you need to have this equal to expected value of delta times pi of delta. Okay. And down here we have effectively the same thing, but for the functionality incentives. Right? So this is again basically the strength of the incentives if the human's actions are independent of their preferences. And then on the right here, we end up with effectively the same term, or we end up with the same term. And what this is it's a measure of two things. I mean, the first one, sigma squared, I think that's pretty clear what that's doing. If the robot is more uncertain, then this is going to be larger, right? And then we have this expected value of pi dot. And that's a little bit harder to interpret. So in order to kind of nail down what this, I mean, we think, what we think it should be is that basically this is a measure of how much uncertainty the robot has. And this is something like a measure of how much the human's shutdown signal reduces that uncertainty. Or at least that's what you would hope. What you can see is it's not exactly that, because this could be negative. So it can't just be, right? It can't just be how much the signal gets more certain. So to look at that, we're going to take basically, we're going to look at two models of irrationality in ways that we could deviate to be suboptimal. And we can see kind of what pi dot is in either of those cases and how that expectation works out. So, yes?
Sorry, could you give a definition of what pi dot is in general?
Oh, sorry. Pi dot is the derivative of pi with respect to delta. Thank you.
Okay.
Yeah, so this is the marginal increase in the probability of shutdown for a marginal increase in the preference for shutdown. And so basically what we want to look at is basically systematic ways that the robot can deviate from that the human can deviate from the optimal behavior. And the first one of these that we'll look at is noisy rationality. As a modeling decision, this basically says that the human is kind of like distracted. So if they really care, or if she really cares, then she will press the off switch and she'll do the right thing. And if she doesn't, she might not. Maybe it's not worth it to go press the button or something like that. And the probability gets pressed sort of increases exponentially as the preference for shutdown increases and falls off exponentially the other way. And it's weighted by this beta parameter here, which is basically what controls how rational the person is. So if beta gets close to 0, then a small increase in the preferences will lead to a big increase in the probability of shutdown. And for beta very, very large, and the limit, beta equals infinity, this is always going to be 0. And so this devolves into a 50-50 choice between shutdown or not shutdown. Yeah?
So your definition of beta, I think, is the inverse of the standard definition. Microsoft Boltzmann beta
is it 1 over
temperature. So it should be beta times delta. I mean, this is just not beta.
Okay, no, that's okay. Yeah, you may be right there. The reason why it's worth looking at this case is because we can actually compute what the derivative is and we can see what it means, right? So the probability of shutdown is going to be a logistic function. And that means that the derivative is going to be well, if we ignored the beta, it would just be probability of shutdown times 1 minus the probability of shutdown. Applying the chain rule means we get a 1 over beta underneath, or we get a 1 over beta being multiplied by it. And what this is this is the variance of the human's policy. So this is giving us, so that kind of, that agrees with the intuition that we have about kind of what this should mean, right? If pi dot is the variance of the human's policy, then this term here turns into the variance in the robot's prior distribution over the reward parameters times the expected variance in the human's policy. So now notice that if one thing you could do here is you could change beta to be negative. And so this would say that basically, for beta approaching 0 from negative, that basically gives you an anti-rational human who's working against the robot, or in some sense, right? And in that case, all of this comes through the same, except we get a negative in front of it. So that means that if the human is actually anti-rational in some sense, so like if this expected value, that means that this expected value is going to be negative, right? So that means we're actually going to pay a penalty in incorrigibility incentives for having higher variance. And that makes sense. Another case that you might have that's worth thinking about is basically just, you could have a human that just has the wrong estimate of her preferences deterministically. So in this case, what's going on is she's overestimating the value of shutdown by beta. Or I guess, no, underestimating it by beta here. And what this tells you is that pi dot is going to be basically a Dirac function, so it's going to be infinite for delta equals beta and 0 otherwise. And what you can see is that this is, so if we have beta equals 0, this is going to be the limit as the variance in that Boltzmann distribution goes to 0 as well. So this deterministic irrationality case is going to move the point where the person sort of is going to move the step function left or right, and that changes the it's still measuring the expected variance in the policy here. Because if you want to look at sort of what this means, you can actually rederive what this is as the limit as the variance of a Boltzmann distribution goes towards 0. That's not too important of a point though. Basically the picture that we get is we have these two policies. We have these two different policies which create effectively probability distributions that look like this. So under the Boltzmann distribution, we've got a low probability for delta less than 0, and then it sort of increases and trends towards 1 eventually. And we have a step function for the deterministic irrationality. And the derivatives here, in one case, we get this kind of bump here. It's 1 over beta times the variance of the policy. And then in the deterministic irrationality case, we have a Dirac delta function, or a Dirac function, let's say. And then we can compute what the expected value of that is, sort of looking at different values of beta. And what we can see is that basically this term falls off as beta increases. So what this is it's a measure of the human's irrationality that's well defined, so it doesn't rely on a relatively arbitrary parameter beta. And it's a measure of that rationality that takes into account whether or not the person is correct or not, and something about their variance in their policy. So it's effectively variance weighted by rationality. And so the final thing that we get from this picture is just looking at sort of the impact of both of these types of suboptimality on the incentives. So in one case, if you have noisy rationality, that's going to both decrease the incentives that you get from being uncertain about delta being less than 0. And it'll also add a negative component because you might behave suboptimally when delta is greater than 0. Whereas for the deterministic rationality, what you get is something that's a little bit more straightforward, where you always get it right down below. And up here, you're going to eat into your incentives as you sort of slide along this axis. So the moral of the story here is that what we need to do is we need to balance the uncertainty the agent has about the human's preferences against the human rationality. So if the person's very irrational and we want corrigible behavior, we'd better make sure the robot is very, very uncertain about what it wants. And that's I'm going to conclude things for me today. So to sum up the sort of 4 main things we talked about, and I guess the main takeaways I have is that I think it's really, really important to be clear and precise about uncertainty in the objectives we give robots or artificial agents, and that incorrectly specifying that certainty leads to problems that I think could be really hard to solve without sort of reintroducing it. We don't know what the right objective to give the agent is, and if we don't represent that information to it, there's no way for it to learn it. We defined a cooperative game that allows us to correlate human-initiated shutdown with the robot learning the correct reward function, right? So, for example, sort of getting back to the question that Stuart Armstrong asked earlier, he said, what does this say about the robot being able to manipulate the probability the person presses shutdown? Well, the extent to which the robot manipulates that action will reduce its correlation with the unobserved reward signal. So if you imagine the sort of most extreme case of this, where the robot just hijacks the person's nervous system or takes complete control of them, then the shutdown action is going to be entirely uncorrelated with the reward signal. And that means that you won't, and what I think that means is that you shouldn't have incentives to try to change the probability the person does one or the other. Except for maybe, you'd rather pick an action that sort of has higher expected reward because you think the person would prefer that one as well. But you're not doing it because it will change the probability they press shutdown. Does that...
I'm just thinking that suppose there's 2 possible reward signals. So 2 words, say.
Okay.
And in one world, the robot is presumably going to get a higher reward than the other. So now what the robot's action is that it moves it from one possible future world to another. Or why not just do it simpler? There's 2 humans who could play the game, and the robot gets to choose which one does it.
So that would definitely be a challenge. And I don't...
Is that the same as influencing one human towards one distribution?
No. And the reason why is because if you influence the human to think that they have a reward estimate that sort of to act as if they have a different reward function that you think is somehow more beneficial, the model still says the agent is getting penalized for that. So the agent doesn't have the ability to manipulate its actual reward signal. Its actual reward signal is sampled at the start of the game and never shown to the agent. Yeah?
What is the difference with the case of 2 humans? In this case, it's not more difficult. I mean, if there are 2 humans, then and the robot believes that both of them have some information about the reward, then it will choose the human that probably has more. It thinks it's more rational.
So if you think that both the humans have the same preferences, then you can treat it like with this formulation and this math. But when I hear 2 humans, the thing that jumps into my head is the humans have different preferences, and so I don't know how to balance those with this kind of a setup. Yeah.
So this seems to assume that the human's preferences are indeed static.
This does, although it's not there. There's a straightforward extension to relax that assumption.
In my head, which might just be a bad model, it seems like if you suppose that later on you change your preferences in a way that makes you want to shut the thing down, it's going to try to stop you, right? If it has enough information to know this, that your previous self would not want to shut it down.
Yeah, I mean, it kind of at this point now, I think the questions are really there are some modeling questions you have to answer once you add that in, and it is true there are different versions of the Searle game. Like one version of the Searle game is that the human's preferences get sampled once. Those are and then if they change over time, you still want to get evaluated against the original one, which would sort of which sort of removes some types of issues. And you could choose to evaluate based on the preferences as they change over time, which could create, in that scenario, you might create incentives to manipulate what the human's preferences are.
So
yeah,
I also have a question, but I wonder if we wanted to finish your conclusion slide first.
Oh, sure. The final points that we have is the first one is that basically increased uncertainty leads to increased corrigibility in this model. And then if the human is suboptimal, the amount of uncertainty needs to grow as that suboptimality grows. Yes, Stuart Russell.
Yeah, you might want to mention that the increased robot uncertainty also can, in general, lead to reduced utility
for the human,
because the robot hasn't a clue what to do. And so there is this trade-off, right? You can't, you can just look at that and say, well, let's just make the uncertainty infinite.
Right.
And then we'll have a super corrigible robot, but of course, the robot has no clue what it's supposed to be doing. It's not very helpful. So helpfulness is a third thing. Corrigibility, functionality, helpfulness.
Yes, I'd like to point that out. Yeah.
So I think this is a fantastic bit of advance that, and then I think, though, for debugging things like this, you think about what happens if your robot is very, very good at thinking about the system.
Certainly.
And the thing that occurs to me is, unless you've chosen your initial distribution P0 very carefully to avoid certain kinds of behaviors, the robot's going to be incentivized to sort of take apart the human and figure out from their innards what theta might have been.
Well, do you think that the human would want that? Because then that's suboptimal in this game.
So the point is that has to be baked into P0.
Yes, right. So you still if you specify there are still challenges this is a mathematical model, and applying it in the real world, there are still challenges like writing down the correct P0 or something like that.
So I think this doesn't include the full challenge of the previous problem, but there's still some mysterious thing here where you don't want to end up writing a blacklist of things in P0. You want something saner about making sure to observe theta only through the human's actions.
Well, so the framework is such that you can only observe theta through the human's actions.
In realistic world models is the trouble.
Yeah, so well, I think there are a couple of things. The first is, I think in terms of human rewards and human preferences, it's not totally clear what those are and how they work and sort of what I'm not sure exactly what space that distribution should be over. So I don't mean to say that this is an end-all be-all solution, but more to point out that if you're not specifying some type of uncertainty, then you're not going to be able to get beyond those kinds of results that sort of show you can either have corrigibility or functionality, but not both. And so that's kind of the main point I want to make. I do agree that if you set this up so that you could give this, this framework doesn't prevent you from giving the robot a point prior, for example. I've done some math to show that that's not a good idea, but there's nothing that precludes it necessarily in the framework. Yeah.
And this was theorem 2, right? And you're selling theorem 2 as a negative result. But to me, it feels like it's kind of the intended behavior, because as the robot learns your reward function and it converges to this point prior or point posterior, then it's going to prevent you from shutting down if you behave irrationally. That's what the theorem says. But this is also what it should do, because that means it knows very well what you want, and you're trying to do something irrational that's trying to stop you from doing that, basically.
Yes, so if you've defined P0 perfectly correctly and you've been able to ensure that your agent does perfect Bayesian inference over the actual preferences, then then that is right, and that's what the model predicts will happen. And I think even there's sort of the case where you're not exactly you're not totally sure, but the human is at least a little irrational, right? So one example I think about for this model is, what if you had a 3-year-old in a self-driving car on the highway, right? That's a case where beta is very large and sigma is pretty low, right? And what we actually want our agents to do in that case is to hide the shutdown button from the toddler, and that's so I view it as in some sense a negative result from the perspective of, we want, from the perspective it says we're trying to design agents that I as an AI programmer can go in and tweak with and modify. But from the perspective of me being a just human-robot interaction researcher, I think that's a total plus, because that's the behavior I would want from my robots. So you're correct. Yeah.
So you didn't talk a lot about the robot outputting different action streams, but imagine you would have different rewards depending on what actions there were as well, and so some way to kind of give this feedback and train it. But if you have a causal structure where theta influences the human in some way, and the human sends some information about the reward to the robot, how do you make sure that the robot is training the right reward and not just something else that's in a roughly similar spot to the causal graph?
That is a really good question. That's where cooperative inverse reinforcement learning is a new framework that we introduced this year, and so we're not quite sure yet. But we have some ideas, at least initially. If you can make some reasonable assumptions about what the human's policy is, you can infer different things. You can do a kind of equilibrium analysis to see, certain behaviors might not make sense in any type of game. But more generally, the problem here is learning with a kind of fundamentally unobservable or non-directly observable reward signal. And I think that's a hard problem that AI capabilities researchers are actively working. The problems of semi-supervised learning and unsupervised learning kind of look like that. This is a different setup, but I would say related.
On meta, can I suggest just at least one more question? At most one more question?
Sure. Yeah.
I'm very impressed because I think this thing is sub-agent stable.
I would need help confirming that, but I also have that suspicion.
It feels that way, which is something I've very rarely seen in this area. We'll have to talk about it one time where I'm awake.
Yeah, of course.
All right, so let's thank Dylan one more time.